Usually when we think about a massive technological revolution, we sort of picture it like building a skyscraper, you know?
Right, yeah, like the very linear process.
Exactly. There's a predictable sequence. You draft the blueprints, you pour the concrete foundation, and then you just stack the steel beams one by one. The path from an empty lot to a finished tower is super visible, and everyone knows exactly what their job
The
is.
structure just goes up floor by floor.
Mm.
And, I mean, if you need the building to be taller,
hmm
you basically just order more steel. It's an exercise in predictable physics.
But if you step into the world of artificial general intelligence, or AGI, that entire construction site is suddenly turned upside down.
Absolutely.
The blueprints are like constantly redrawing themselves, the materials keep changing shape, and right when you think you just need a massive delivery of steel to finish the top floor, you realize the entire multi-billion-dollar project is actually bottlenecked by, and this is the crazy part, a desperate shortage of interior decorators.
That is a brilliant way to put it, because we are attempting to build, essentially, the most complex cognitive structure in human history.
Hmm.
And we are quite literally figuring out the physics of it as we go.
Yeah, build in the plane while flying it.
Exactly. And the bottlenecks we anticipate, they almost never end up being the actual roadblocks.
And that dynamic is exactly what we are dissecting in this deep dive today. We are trying to cut through the deafening noise about AI to trace the actual pragmatic roadmap of how we reach AGI.
Right? Like, what are the mechanical transitions happening under the hood right now?
Yep. And critically, what does this mean for your future job, your daily workflows, and the world we're building for the next generation? We are mapping this out using a really fascinating source today. It's a Y Combinator interview with Bob McGrew,
He was the former chief research officer at OpenAI.
which is huge.
It really is. Bob's perspective offers a rare vantage point because, well, he was in the room for the foundational decisions that shape the modern AI landscape we see today.
Yeah, he was right there in the trenches.
We are exploring the algorithms, certainly, but more importantly, we're looking at the cultural and philosophical shifts that allowed those algorithms to be discovered in the first place.
Right. And we're going to cover everything from robots wrestling with Rubik's Cubes to the industry's strange obsession with a skating pink panda to the actual structural reason why an AI agent hasn't completely taken over your laptop job yet.
A lot of ground to cover.
It is. But to understand where this technology is rocketing toward, we really have to rewind to how it got off the ground. Because the biggest initial breakthrough wasn't some elegant math equation, it was a structural decision about how to run a workplace.
To set that scene, you really have to look back at 2015. So Bob McGrew had just left the software company Palantir, and his intention was to start a robotics company.
Wait, robotics, not software.
Yeah, he firmly believed robotics would be the first major commercial success built on deep learning. He actually taught a robotic system to play checkers using purely visual inputs just to learn the mechanics. But he quickly hit a wall. The underlying intelligence simply wasn't ready to handle the chaos of the physical world yet.
So it's just too early.
Exactly.
Sure.
So he pivots and joins OpenAI, which at the time had this incredibly ambitious mission to build AGI, but they were operating with a rather flawed initial strategy.
Flawed how?
Well, they were essentially functioning as an open-source research lab, just churning out academic papers.
Okay, let's unpack this. Because the culture of the major AI labs at that time was deeply divided.
Very deeply divided.
You had DeepMind on one side, which operated with a very top-down, centralized, almost military structure. The leadership pointed at a hill, and the entire company marched up it.
Right.
And then you had Google Brain on the other end of the spectrum. Their approach was basically to rebuild the academic ideal inside a corporate shell.
Yeah, they hired the most brilliant minds, gave them unlimited server access, and basically said, let 1,000 flowers bloom. Research whatever fascinates you.
But OpenAI realized neither extreme was really going to work for them. They modeled themselves after a highly focused startup trying to win a championship, rather than a giant sandbox where solo athletes just padded their individual stats.
They engineered a highly effective happy medium. They rejected the rigid centralized plan, but they also recognized that purely exploratory research sort of dissipates energy.
You just spin your wheels.
Exactly. So they leaned on highly opinionated leadership figures like Ilya Sutskever, who directed massive resources toward a few specific large-scale bets.
But implementing that focus required solving a pretty toxic cultural problem, right? Something a lot of researchers brought over from academia.
Yes, the absolute obsession with individual credit.
Right, because in the academic world, Being listed as the first author on a groundbreaking paper is like your currency. It dictates your tenure, your funding, your entire career trajectory.
And that specific incentive structure actively destroys collaboration. Well, think about it. If a researcher has a breakthrough insight, they are financially and professionally incentivized to hide it from their colleagues so they don't lose that prime authorship spot.
Oh, wow. Yeah, that makes sense. You wouldn't want to share your homework.
Precisely.
Yeah.
So OpenAI made a radical intervention. On their early robotics papers, they simply cited OpenAI as the primary author.
Just the company name.
Yeah. They deliberately stripped the individual ego out of the equation to force internal teamwork.
And stripping away that ego is what allowed them to throw all their weight behind a couple of seemingly crazy bets. They dedicated entire teams to two primary projects.
Right.
First, trying to teach a robotic hand to manipulate a physical Rubik's Cube. The theory there was that the physical world is so unpredictable that AI would be forced to adapt and generalize its learning outside of its highly specific programming.
Which is a huge hurdle.
Massive. And the second bet was trying to beat professional human players at the intensely complicated video game Dota 2.
What's fascinating here is how those two specific games laid the invisible foundation for the AI we use today.
Yeah, Dota 2 specifically, right?
Yeah, because Dota 2 is mathematically chaotic. It requires long-term planning, deception, teamwork. And by throwing vast computing resources at Dota 2, OpenAI proved the fundamental secret of the current AI boom, which is scale.
Just pure scale.
Yes. They discovered that if you feed gargantuan, like unprecedented amounts of experience into a neural network, the system doesn't just memorize the game board. It learns to generalize.
It develops an intuition for the mechanics of the environment.
Exactly.
And while the Dota and Rubik's Cube teams are proving that scaling up the computing power creates intuition, there is another researcher, Alec Radford, who's quietly experimenting with language models.
Right, and Alec was working with a staggeringly simple objective, predicting the next token.
And in AI terminology, a token is essentially just a chunk of a word, right?
Basically, yeah. So his model was literally just reading text and trying to guess what the next few letters should be.
Which sounds so basic.
At the time, the broader industry thought this was far too simplistic to generate real intelligence. But Alec persevered, and that predictive engine became GPT-1.
Wow.
And the opinionated leadership at OpenAI then recognized a synergy. They took the lessons of massive scale learned from the Dota 2 servers, and they applied them to Alec's word-guessing model.
Fusing that simple token prediction objective with gargantuan computing power. And that led directly to the exponential leaps of GPT-2, 3, and 4.
That was the secret sauce.
So scale is the magic ingredient, I guess, assuming you have a foundation that actually works in the first place. Because you can't scale a broken model and expect it to suddenly become a genius.
Right. That is the catch. Getting a model to that initial baseline, getting it to step one, is a notoriously agonizing process.
The 0 to 1 phase.
The 0 to 1 phase, and we often gloss over how painful it is. Take DALL-E, OpenAI's image generation model.
Right.
Researcher Aditya Ramesh spent between 18 and 24 months tweaking the architecture just to get the model to generate one highly specific image.
And this is the famous pink panda, right?
Yes. A pink panda skating on ice.
And I can guess why he chose that specific prompt. Because you can be absolutely certain there are no photographs of a skating pink panda in the millions of images used to train the model.
Precisely. It doesn't exist. If the model can generate that image, it proves a fundamental leap in intelligence.
It proves the system isn't just regurgitating a memorized photograph of a panda. It is actually understanding and combining separate abstract concepts, pink, panda, skating, ice, in a completely novel way.
Yes, and it took up to 2 years of failure just to get a blurry, barely recognizable amalgamation of those concepts. But the moment you get that blurry image, the moment it plausibly works, you have reached step one.
And that is when you unleash the scaling laws.
Exactly.
Which scaling laws essentially mean you have two distinct levers you can pull to make the model smarter, right? You can use brute force, just throwing more server farms and massive amounts of data at the problem.
Right, that's lever one.
Or, lever two, you can change the slope of the curve by finding a more efficient mathematical architecture, allowing the model to learn more from the same amount of data.
And once you hit that 0 to 1 proof of concept, pulling those levers makes progress highly predictable. The model gets exponentially better.
But those levers rely on a finite resource, don't they? Which brings the industry to a massive looming bottleneck.
Yeah, they are hitting a data wall.
A data wall.
Because these models require pre-training, which is the initial phase where the AI reads billions of documents to learn the patterns of human language.
Right.
The stark reality is that we have essentially vacuumed up the entire internet. The high-quality human text needed to fuel that specific brute force engine is just running out.
Wait, if the machine has read all human text and there is literally no more high-quality data to feed it, doesn't the math dictate that this exponential progress has to plateau right now? Like, if the fuel is gone, the hype train has to stop.
On the surface, yeah, that is the logical conclusion. But look at the history of computing, specifically Moore's law.
The consistent doubling of computing power.
Right. Analysts have been predicting the death of Moore's law for decades. And they were always wrong because they viewed it as one continuous curve.
I see.
In reality, technological progress is a series of smaller S-curves. You push one specific mechanism like shrinking the physical size of transistors until it hits the laws of physics.
You hit a wall.
You hit a wall. But the pressure of that bottleneck forces the discovery of a completely new mechanism, like multi-core processing, and the exponential growth simply jumps to a new S-curve and continues.
Okay, so if the old S-curve was read the entire internet during pre-training, what is the new S-curve that allows these models to keep getting smarter without needing more data?
The new S-curves is driven by two concepts, reasoning and test-time compute. This is the fundamental shift we are seeing with models like OpenAI's O1 and O3.
So how is that different from before?
Well, under the old paradigm, a model relied entirely on its pre-training. It was essentially using muscle memory. You asked a question, and it immediately spat out an answer based on patterns it memorized months ago.
Just instant recall.
Right. But test-time compute changes that completely. It gives the model a mental scratch pad at the exact moment you ask the question.
So it's actually pausing to think rather than just reacting.
Exactly. It generates a hypothesis, spots a logical flaw in its own reasoning, backtracks, and tries a completely different path before ever showing you the final output.
Wow.
So the bottleneck shifts entirely. It is no longer how many encyclopedias did you read. It becomes how much computing power and how much time are we allowing you to spend thinking about this one specific problem.
Here's where it is really interesting, because this new S-curve of reasoning isn't just about making the AI better at solving complex math puzzles, right? This internal monologue is the exact mechanism required to unlock AI agents.
Yes, systems that can navigate the internet, use software, and take reliable action on your behalf.
Because the concept of an autonomous agent doing your digital chores has been promised for years, but it has never been reliable enough to deploy.
No, it hasn't.
Yeah.
Because if you ask an agent to research 5 vendors, compare their pricing tiers, and, draft a contract, it cannot hallucinate a number halfway through the process.
Right. A human will not wait 5 hours for an AI to complete a complex workflow if there is even a 10% chance the final output is completely unusable.
Exactly. The math on achieving that reliability used to be incredibly prohibitive.
This is the nines problem, right?
Yeah. The industry rule of thumb was that to add a single 9 to your reliability, meaning to go from 90% reliable to 99% or 99 to 99.9%, you had to increase your overall computing power by a massive factor of 10.
You had to train a model 10 times larger just to squeeze out that tiny margin of safety.
And that approach was financially ruinous and agonizingly slow. But reasoning completely alters that equation.
How?
Models can now achieve that extra 9 of reliability simply by thinking longer during test-time compute. This breakthrough flips the script on what AI is capable of executing autonomously.
Which brings up a historical mystery that Bob pointed out in the interview, dating back to 2018.
The AGI timeline mystery.
Right. Back then, the assumption was that the moment an AI could pass the Turing test, write flawless code, and generate photorealistic images, the economy would instantly flip. All laptop-based jobs would be automated overnight.
And we currently possess all of those capabilities.
We do. So why is the actual integration of AI in the corporate workplace moving at a relative crawl compared to the technological hype?
Bob traces the answer directly back to his early days at Palantir. They learned a really harsh lesson back then. Raw intelligence, or possessing massive oceans of data, is functionally useless on its own.
Useless?
Well, imagine a team of government intelligence analysts trying to track a global threat across 20 disconnected databases.
Oh.
Palantir realized that handing those analysts a slightly smarter, faster database didn't actually solve their daily friction.
It didn't change how they worked.
Right. What they desperately needed was a completely reimagined interface. So Palantir succeeded by deploying what they called forward-deployed engineers.
Forward-deployed engineers.
Yeah, basically software developers who would literally sit at the desk next to the client, watch exactly how they click through their day, and build a highly customized software UI that solved their exact messy workflow.
Okay, so having a super intelligent large language model, or LLM, right now is kind of like having a genius brain floating in a jar on your desk.
That's exactly what it is.
It is brilliant, it has read every book ever written, but it has no nervous system and no hands. It can't actually do your job because it is not cleanly connected to your specific email client or your company's proprietary database or your unique daily schedule.
The software interface, the UI, is the nervous system.
And that nervous system is the current missing link in the AI revolution.
Without a doubt. We do not necessarily need a smarter brain in the jar right now. What the industry desperately needs is an army of traditional software engineers building tailored interfaces that link that raw floating intelligence to actual human problems.
So the true bottleneck for AI adoption is the lack of human-centric software built around the models.
Absolutely.
Which, if you are an entrepreneur or a leader trying to integrate AI at your company, that is a massive strategic opportunity for you. The gold rush isn't in trying to train a new, smarter LLM from scratch. The gold rush is in building the nervous system.
Spot on. But Bob had some very counterintuitive advice for founders on how to actually build those products.
But what's his advice?
His mandate is to start prototyping your product using the absolute best, most expensive, cutting-edge frontier model available.
Wait, really? Just ignore the computing costs in the beginning?
Ignore them. A startup's most valuable asset is not its server budget. It is time. You must prove that your core product actually works and provides undeniable value to the end user before your runway disappears.
See, if I'm a scrappy startup founder with limited funding, my immediate instinct is to use the cheapest, smallest open source model available just to keep my overhead low while I tinker.
A lot of people think that way.
But I see the trap there. If my prototype fails, I have no idea if my underlying business idea was flawed or if the cheap model just wasn't smart enough to execute it.
Exactly. By using the genius level model, you validate the core business logic immediately.
Okay, so you use the genius model to prove the concept works. Then what? Because I hear the word distillation thrown around constantly in these startup circles, and I immediately think of, like, boiling a complex liquid down to its absolute most potent concentrated form. Is that what we are doing to the intelligence?
If we connect this to the bigger picture, your analogy is spot on. Distillation is a master and apprentice dynamic.
Okay.
You take your incredibly expensive, massive frontier model, and you force it to teach a much smaller, radically cheaper model how to execute one highly specific task flawlessly.
Oh, I see. You boil the broad intelligence down into a concentrated, highly efficient workflow.
Yeah, and this process turns cutting-edge intelligence into a cheap commodity service. It means founders should focus entirely on solving the user's friction perfectly during prototyping, knowing they can aggressively crush their server costs later through distillation.
That mindset shifts the entire strategy of building an AI company. So we have the digital world mapped out. We are building custom software interfaces to allow reasoning agents to automate our digital workflows.
Right.
But eventually, we need the AI to reach out and touch the physical world, right?
Which is the hardest part.
Yeah, and Bob highlighted a fascinating physical bottleneck on the horizon. We are approaching a point where AI models operate as level 4 innovators.
Basically meaning they will possess the capability to generate brilliant scientific hypotheses and design complex lab experiments completely autonomously.
But the intelligence will be moving at the speed of light, while the actual execution will be trapped moving at the speed of human hands.
Right. We will have models inventing new chemical compounds in seconds, and then we will be stuck waiting months for human lab technicians or incredibly rudimentary robots to physically mix the liquids and run the trials.
So we are circling right back to the exact realization Bob had in 2015 when he abandoned his robotic startup. The physical world is the ultimate friction.
It is the final frontier for this technology. And the broad consensus is that the robotics industry today is sitting exactly where large language models were 5 years ago.
Ah, so they are trapped in their own agonizing 0 to 1 phase.
Exactly. They are trying to achieve the physical equivalent of generating the skating pink panda.
Just getting that first proof of concept.
Yep. But heavily funded companies, like skilled AI and physical intelligence, are currently building foundation models specifically for robots.
So the timeline is accelerating.
Huge acceleration. The prediction is that we will experience the ChatGPT moment for robotics within the next 5 years.
Just 5 years.
Yeah. And once that physical bottleneck breaks, the pace of scientific and material advancement will be almost incomprehensible.
Wow. Okay, so the timeline looks like this. Reasoning agents take over our digital workflows in the immediate future. And within 5 years, a robotic revolution begins handling the physical world.
That's the roadmap.
Where does that leave us? Bob painted a picture of a hyper-personalized future where you have an AI bot that has ingested your entire digital life, your preferences, your communication style, your calendar.
You could literally consult a colleague's digital bot to see how they would react to a pitch without ever bothering the actual human being.
It is a staggering level of personalized leverage, but it inevitably begs the ultimate question regarding human purpose and education, doesn't it?
It really does. And Bob shared a personal anecdote about his 8-year-old son, who currently wants to build an asteroid mining company.
A very ambitious 8-year-old.
Very. And every evening, Bob uses AI models to generate custom curriculums to teach his son how to write traditional software code.
Hold on. If an AI can already write flawless code in seconds, and in 5 years it will be a super intelligent, autonomous agent, isn't teaching an 8-year-old to manually code today the exact equivalent of forcing them to use a slide rule or a physical abacus?
That's the obvious pushback.
Like, what is the actual utility of that skill?
This raises an important question about the fundamental mechanics of how human beings learn to think. Bob leans heavily on a concept from the programmer and essayist Paul Graham called the resistance of the medium.
The resistance of the medium, what does that mean?
Well, when you sit down and physically wrestle with writing code, when you build something, watch it break, painstakingly debug it line by line, and feel the frustration of a missing semicolon, you are not just producing a digital product.
You are forging the neurological pathways of critical thinking.
Exactly. You are developing a deep, intuitive understanding of the logic of machines. You have to wrestle with the physical and mental resistance of the medium to develop the raw problem-solving skills that AI will eventually supercharge.
So what does this all mean for our careers? You're training the mind to understand the architecture of problems, rather than just teaching it to produce a final product.
That's it. And Bob sees this philosophical shift leading to 2 primary job descriptions for humans in the coming decades.
Okay, what are they?
First, the lone genius. This is an individual working entirely alone, but heavily leveraged by a suite of AI tools to execute the output of 100 traditional employees.
Wow, just a one-person powerhouse.
Right. And second, the manager, someone who essentially acts as the CEO, directing and coordinating a firm composed almost entirely of AI agents.
That paradigm shift sounds unimaginable to most people today.
It does, but Bob uses a brilliant historical analogy to ground it. In the 1880s, the vast majority of the human population were farmers.
Right.
If you traveled back in time and tried to explain the daily life of a modern software engineer or a digital marketing consultant to an 1880s farmer, it would sound like absolute nonsense to them.
They wouldn't even possess the vocabulary to recognize it as a real job.
Exactly. We are those farmers right now. We cannot possibly predict what the daily granular jobs of our grandchildren will look like. We will have to remain radically adaptable as the ground shifts beneath us.
If we are the 1880s farmers, then our entire definition of a career is likely about to become obsolete, which means preparing our kids isn't about teaching them a specific trade, it's about teaching them radical adaptability.
Beautifully said.
To wrap up our deep dive today, we have journeyed from the unique, ego-stripping culture of early OpenAI that allowed them to make giant bets on scale, to the agonizing process of pushing DALL-E to generalize a skating pink panda.
Right.
We've seen how hitting the data wall wasn't an endpoint, but the catalyst for a new S-curve of test-time compute. And that reasoning is what finally unlocks reliable agents.
The big unlock.
But we also learned that those agents are just genius brains in a jar until forward-deployed software engineers build the UIs to connect them to our messy reality. And while the physical world waits for its own robotic ChatGPT moment, we are left preparing ourselves to be the lone geniuses and managers of tomorrow.
Tracing the actual mechanics of these transitions really removes the magic and replaces it with a tangible, actionable roadmap for the future.
It provides immense clarity, but it leaves me with one final provocative thought for you, the listener, to mull over.
Let's hear it.
If the future dictates that we are mostly managers of superintelligent agents, and we no longer have to struggle with the resistance of the medium to create things, will we eventually start manufacturing artificial difficulties for ourselves?
That's interesting.
Like, if the AI can instantly build the skyscraper for us, flawlessly, will we force ourselves to draw the blueprints by hand anyway, just to satisfy that deeply human need to overcome a challenge? It is definitely something to chew on as you navigate the AI revolution.
The capabilities of our tools will completely transform, but the core human drive to wrestle with the world remains exactly the same.
Thank you so much for joining us on this deep dive. Keep questioning the blueprints, keep connecting the dots, and we'll catch you next time.